everyone. Welcome to the second session of today's Simpa School. Now, our next speaker is Meruna. Meruna is going to be her last lecture officially, but afterwards she will continue as in the tutorial, explaining more about the keywords. Over to you, Meruna.
Hello, everyone. I'm sharing now the slides. Can you see the screen?
Yeah.
Okay. So thank you very much. I am happy to give it's the last lecture, but I'm looking forward to the tutorial, which I'm sure will clarify many of the things that we saw, and especially from last lecture that I wanted to see more in detail how to compute and how to prove those disguised toric loci. But I thought it's better to go to the next subject, and then we go in a couple of hours we will see the computations from those previous slides. So this talk is about a fine equivalence of reaction networks. So this is my fifth talk, so it's okay. What is the overview? I just want to recall previously what we saw. We saw all the terminology, some properties of reaction networks and of toric dynamical systems introduced by Crăciun, Wittgenstein, Schiu, and Sturmfels. So that we reached in the end to understand what is the disguised toric locus. That was one of the goals. And previously we saw for the triangle on a line how to compute it, the disguised toric locus. We saw that the toric locus was a dimension 1 variety, but intersected with a positive order. But then we, by using dynamical equivalence, we saw that actually for all reaction rates, so for all Ks that decorate the edges, the system is coming from this network is complex balance. So we saw a difference between Lebesgue measure sets between the toric locus and the disguised toric locus. We checked the quadrilateral on a line also, which is gonna be detailed in the tutorial. And also during the tutorial, I would like to mention briefly the n-gon on a line, because that's the generalization of the triangle and quadrilateral. And then we will also see an example of a case where the toric locus is empty because the network is not weakly reversible. So the combinatorics of the network stops it from having anything in the toric locus, but actually the disguised toric locus is a positive Lebesgue measures. And also we will see an algorithm that one can apply in order to study more classes of networks and more to find new results, because we just consider several networks or families of networks, and there's still a lot more to find out about the disguised toric locus. And precisely because of this, because this is what motivates this lecture. Sorry, this was supposed to be 5 here lecture. So we will now look at what happens with the disguised toric locus if we apply invertible fine transformations to the network. So essentially, since computing the disguised toric locus is non-trivial, we would like to use some other tools to simplify this task. I was planning also to talk about the topological structure of the toric locus, because there are two preprints that together with Crăciun and G, we studied the toric locus topologically. Probably there is not time for that, and I invite you to read them. Essentially, we showed that the toric locus is connected, and even more, it is a smoothly embedded submanifold of the Euclidean space. That's just a further reading, invitation to further reading. So what is the motivation of this lecture? Essentially, we want to know the answer to the following question. How does the geometry of the network influence the qualitative long-term dynamics? So we would like to see what we can answer from this question. And how can we take advantage of the geometry to infer directly some answers about the long-term dynamics of the system. Recall, for a fixed network, the disgastory locus is the set of parameters such that the resulting system is dynamically equivalent to a complex balance system. But the disgastory locus is quite poorly understood when compared to the toric locus, where the work by Crăciun, Dickenstein, and Stunfels clarified the codimension and everything. And why I say it's quite poorly? Well, even for the quadrilateral on a line, remember it was we saw last time so in order to completely describe the dynamics of this network, we had to divide the parameter space in 4 chambers. If you remember, there were those reactions that had 1 reaction per source, and even for the last chamber, there were some other nonlinear condition that the parameters had to satisfy, and so on. We'll see in the tutorial. So it's quite involved even for such a simple 4 vertices on a line, but doable. So now we want to simplify the task of computing the disgastory locus. How? We related the locus to a different network. In a different way. So essentially, we will use a fine equivalence of reaction networks and see what that gives. I think it's a good recap here to recall what is an invertible affine transformation, mostly for fixing notations during the talk. So we have, if we denote by A, okay, so this is how we will define during the talk invertible affine transformations from Rn to Rn. How we define A? So we consider an invertible linear transformation M and a vector B, translation vector in Rn, and that's the shape A of Y, and it's the classical notion of affine transformations, invertible ones. And now, what do we call the image of a network by an invertible affine transformation A? I think it's quite intuitive now that every vertex, so we take the set of vertices of G, of the initial network, apply A, and take this set A of V that has all the images of the vertices by A, of the vertices of the network G. And for the edges, so the set of edges of the new network, we just connect now these images obtained before.
Excuse me, are we assuming that this is a E-graph, the network?
Yes, we consume, we assume, yes, it is Euclidean inverted graph, E-graph, yes. Actually, there is here a small observation. We even look, so previously I was mostly thinking of E-graphs such that the vertices had integer non-negative coordinates. But here is a slight generalization. Because it didn't there was nothing to stop us to consider generalized network in Rn. So you can even think of vertices so any real numbers, real coordinates. But we can always think just in the setting of before. And thank you for the question. And the image now is just this new graph. So it's simple. Now we talked about the graphs, but if we look in the setting of mass action kinetics, so first of all, we just considered graphs and the image of such a graph, also called, so graphs also called networks, by such an invertible affine transformation. So I have G and A of G. So abstractly, A induces an isomorphism of graphs, but we want to work with mass action kinetics. So what happens with the rate constants now? So we just define in this way. We assume that all the rate constants are inherited. We just use the same rate constants. And here is the definition. We say that two networks are affinely equivalent if there exists an invertible affine transformation. Okay, so such that these graphs are, the G prime is the image of G through A. And now I'm just saying here that we keep the rate constants K decorating the edges. And then we say that these systems are affinely equivalent if the graphs are affinely equivalent.
Excuse me, Miruna.
Yes.
Can't we say what is the difference if one address that if the two graphs are isomorphic to each other, then we can say that they are affinely equivalent, or isomorphism of the graph is too much, or you are taking into account some distances or isometry or something between the graphs?
Thank you for the question. Actually, it is maybe if I say some more, might be clear, because we maybe we get to this why we consider invertible affine transformations, right? That's maybe what you are.
Yeah.
Why
And
precisely this class, right?
Yeah, why precisely this class? And regarding to the question what Sam asked, if we are considering it as a graph, then what about the graph isomorphism? So whether the graph isomorphism and the applies the affine equivalence or not?
I'll leave the answer a bit for later if that's and maybe it will be clear soon, because I prepared some slides on motivating why we look at this. But if not, we will come back.
Okay.
I hope. If not, please interrupt me again after a couple of slides.
Okay.
So before I explain why we look at these particular transformations, let's see some results, but just roughly speaking, then it can be made more precisely. So the disguise, it turns out that the disguised storic locus is preserved indeed under invertible affine transformations of the network. So that's very good, because recall the disguised storic locus is about dynamical equivalence. So it's about having the same dynamic, controlling the dynamics, and that's the cornerstone of what we are considering here. We want to control the dynamics, not anything else. So that's very good news. Moreover, from the computational side, it is great that we can compute now the disguised storic locus. For instance, if you have a complicated network or we are a bit more involved, you just take an affine transformation of it, and if you know to compute the disguised storic locus for that one, you are now set. You don't need to do anything else, because the disguised storic loci are the same. And yeah, we will see during the tutorial for this left-hand side network to compute the disguised storic locus. It's a positive Lebesgue measure. And then directly, maybe I even wrote here, no, directly we know for the right-hand side. Before I motivate what I was promising, just I want to say one more. So more general, invertible affine transformations preserve the property of two networks being dynamically equivalent. So that's actually what helps us say the previous thing about the disguised storic locus. Good. Now, maybe this will answer the question, but if not, let's see. So why do we consider invertible affine maps? One property of affine maps here is that, so as graph isomorphism, is that they preserve collinear vertices. That's a property of invertible affine maps, not only of those, but first of all, what does this mean? What do I want to say? So you might wonder if preserving collinearity of vertices is necessary for the preservation of dynamical equivalence. So when I say here preserving dynamical equivalence means that if a network is dynamically equivalent to another one, then their images respectively are dynamically equivalent. We'll write this more rigorously. But now, why? Do you think it's necessary for preservation of dynamical equivalence to preserve the collinearity of vertices in the network? Well, we have an example showing that indeed this is a necessary condition. So this is one of the reasons why we look at these transformations. So in this example, we have the network from the left-hand side, A, and if you play a bit with the ODE system, if you change the rates, okay, you can see that you can make longer the reactions, right, the vertices, the vectors, and you can actually rewrite the ODE such that the network in the left-hand side is reversible. And you already saw, I also mentioned, and I think just the previous lecture by Beatrice also, so the definition. Each reaction has its reverse reaction. I wrote here. So the left reaction here is dynamically equivalent to a reversible network. You can check this by finding such a reparametrization of your rate constants. But let's take a map, the map xy sending, so the map sending xy to y, comma xy. So a map that here does not preserve collinearity. And it turns out, if you try to decompose here the vectors and to find dynamical equivalence with some new network that has the same ODE system, you will never get a reversible network. So this right-hand side network is never dynamically equivalent to a reversible network. In other words, this map, xy and yxy, did not preserve dynamical equivalence of the networks. And this shows that there is a problem if you lose the collinearity of vertices. That's one of the motivating reasons to work with invertible affine maps. But maybe this is also your question, if I understand correctly. I'm not sure if that's what you were wondering, but we also ask now, okay, these invertible affine maps are good, but what is the largest class of graph isomorphisms that can preserve the disguised toric locus? So since we know that collinearity is necessary of the vertices, we might also think that invertible projective transformations that also preserve collinearity are a candidate for our interest of preserving the disguised toric locus after applying the transformation.
Sorry,
Or maybe we can...
just probably unrelated question, but the network in the previous slide is of course not directly reversible under the definition that Beatrice gave. So how do we know, well, in general, if a network can be reparameterized, a non-reversible network can be reparameterized to make it reversible? Do we know something like that?
Yes, I'm not sure now of a general result. Here we just tried here, but there might be some. I'm not sure.
Okay, thank you.
I can check and tell you maybe during the tutorial. Here we were just trying for this precise one.
Thank you.
Okay. Thank you. So what about considering projective transformations, invertible projective transformations? Do they work? And in other words, we can say, is collinearity, preservation of collinearity sufficient also? Because necessarily we saw it is. So is it sufficient for this? And part of our results is also discussing what happens, mostly giving counterexamples to. So there is a section of this in this context of projective transformation. In that section, there are negative results in the sense that we show with examples that invertible projective transformations preserve neither dynamical equivalence nor complex balancing, nor the property of being disguised tonic. Maybe I didn't make this clear. I want to underline the fact that this whole results, all this talk for today is coming from this paper article, The Disguised Historic Locus and Affine Equivalence of Reaction Networks. This is by Hake, Satriano, myself, and you. It's published, and all the details that I skip today can be found here. So maybe I didn't make this very clear. Maybe you can read all other arguments that are not here in the paper. Okay, go back. So we see here that projective transformations are not what we want, and are not helping us in any case for any of these properties. And I'll show examples in the slides later. So this, I would say that as a conclusion, that the class of invertible affine transformations are the most natural graph isomorphisms when we want to study dynamical equivalence and disguised historic systems. I would say that that's the reason why we look at these transformations. Okay, moreover, affine transformations also preserve some structural features of networks, of course, so just from the network. For instance, the property of being strongly endotactic. What is being endotactic first? So there is no reaction, so considering the network, reaction is endotactic if there is no reaction that points outside of the Newton polytope of the network. So outside the convex hull of the network. And strongly endotactic, let's see, there is one more condition. For now, let's go into details, but these networks are known, and some references there are in our paper. You can read some more of these of the dynamical significance of being strongly endotactic. So what I want to say is that affine transformations preserve some structure that has dynamical meaning, the structure of the network. So that's why we also asked if there are some other properties that are preserved by such network transformations. Besides what we saw, the disguised historic locus, dynamical equivalence. What else from the dynamics can we preserve once we apply the affine transformation? This is the question. Are there other qualitative dynamics preserved by invertible affine transformations of networks? So maybe let's think outside of this context of disguise in general. Or differently put, how are the dynamics in general of affinely equivalent mass action systems related? And we proved with Hake, Adriano, and you that actually, there's the good news, there is a canonical bijection, I will give it precisely, between the sets of positive steady states of affinely equivalent mass action systems. So we know that the set of positive steady states are preserved bijectively. This we will see also with examples that this does not imply in general also that the properties of those steady states are preserved, like such as local stability. Moreover, since you saw also today a previous lecture about multistationarity, I remember, and I also mentioned last time, neither the capacity for multistationarity is preserved, and I'll show an example soon. And maybe you'll think maybe some limit cycles also, if the steady state, the positive steady states are preserved, what happens with the limit cycles? Turns out that they might also disappear. So this is interesting. Turns out that it is not necessary for a finely equivalent mass action systems to share the same qualitative dynamics, unless we have this complex balancing from before that we saw. This guy's Toriclochus is preserved, and remember that for complex balancing, we have very nice dynamics, we have unique, locally stable equilibria up to conservation law, so in each stoichiometric compatibility class. So because the sets of positive steady states are bijectively preserved, that's why it works so well for complex balancing. So this was the whole introduction, motivation, why we got here, why we work with these networks, what we found out, and also why we cannot extend from fine transformations to projective transformations in what we are interested in complex balancing, in this guy's story. So for the
Sorry,
second part of, yes.
Am I right in assuming that under these fine transformations, the stoichiometric subspace will stay invariant?
We'll see in the examples, they change. I have an example where we'll see this. Okay. So now we are ready to go into the details. So just to see more rigorously and the examples I promised. The second part of the talk. The third part will consist of the counterexamples for the projective transformations. Okay. So again, just to remember the notation k hat of G, this is this guy's Toriclochus of G. We usually use this notation. I remember there was a question last time. We consider k hat, we usually write k hat of G, even if there was a question why we, let's stay with this, just to know from which, somehow to keep maybe track from which reaction did we start to get the system. And here is the more rigorous statement. So we have a network, any network G in Rn, take any invertible affine transformation A of Rn, then we have this result that these guys' story loci are the same. So the k hat of the image, A of G, is k hat of G. To be more precise, so even more, okay, so you can see it this way. If we have G dynamically equivalent to another G star, okay, here you see with different rates, different parameters, reaction rates, this is K and alpha, then the images of G respectively G star are also give also dynamical equivalent systems. And if G star is complex balance, then its image by the invertible affine transformation A of G star with the same, again, as usual, same rate. So G star and A of G star with the same alpha rate constants. Then we also get the images of complex balanced. So here is here are all the properties that we mentioned before. So it preserves dynamical equivalence, it preserves complex balancing, and we then obviously see that it preserves this guy's Toriclochus. for this concrete example that I was showing before, let's see what was the affine transformation. Here it's we took this linear transformation of the network. So here is a lot of place to keep playing with these kind of transformations, and maybe you discover some new properties. That's why I wanted to show these two papers, and I think there are more things to discover, maybe in some different directions. And I'm happy if you listen and are interested in this. Maybe you can continue this line of research. So here we have this network. We take a linear transformation that's invertible, and in the tutorial we will need to compute this disguised toric locus k hat of g, showing that it's the set of parameters k positive in R4 that satisfy these two inequalities. In the tutorial, actually, we have a more general shape of such network where we allow the angles to vary and the lengths as well. The length of, you see here is a rectangle given by the vertices, and it's a 3x2 rectangle, but we will have a generalized formula for such rectangles with any lengths and any angles varying of the networks. But again, it will be very similar. It will be a generalization of such a set that is a positive Lebesgue measure during the tutorial. So here, quickly, we deduce that the right-hand side also has this disguised toric locus just by our theorem. But now, what happens? We stay with these two networks. What happens? Okay, fix some case, fix a vector of rate constants, k1 up to k4. Let's say they are all 1 to simplify the computations. And what happens with the steady states? Concretely, because I already announced. Here it's what happens. In the right picture is the initial networks, the phase portrait of the trajectories, okay, from the initial network, and the left picture is the phase portrait of the finely invertible transformation of our network. Here there are some more explanations. They are disguised toric, so we know that they have nice dynamics, just a locally stable steady state, and you see that it's globally attracting in this case. But indeed, the steady states are preserved bijectively, and this can be made precise in the theorem now. So what I was saying about this bijection between the positive steady states, we need the notation here. Denote this. Here we have a vector x and the matrix M from what we saw before. This is our invertible matrix. Then we denote x to the m by this column vector. Why we need this? Because now we need to understand which is the image of the steady state of the transformed network. So consider an invertible affine transformation given as before by this formula, where M is as before, okay, invertible. And if we have a positive steady state of our network with the rate constant k, denoted by x, we prove that the value x to the power m, where we have this notation, is a positive steady state of the here. Okay, here we just took the opposite direction. Sorry, we start with the, otherwise we would have taken the inverse. Okay, start with the positive steady state of this, and its pre-image has the positive steady state is to them. So this is the bijection that I was talking between the positive steady states. Now, again, the question is, does this bijection or this result imply that we also preserve asymptotic stability? Do we also preserve the capacity for having multiple, multiple steady states on the same compatibility, stoichiometric compatibility class? And also, do we preserve the existence of limit cycles in under affine transformations? And here the promised examples appear. So we have that first thing. Affine transformations, turns out they do not preserve multistationarity. So here are the compatibility. So you have first this network from beginning. We apply this affine transformation A of y given by this matrix and this vector B in this expression. And then you get the network from B, from the picture B. And here is, so I think that was, so I was referring to this example about changing of the stoichiometric compatibility classes. This shows that they change. And also we highlighted in yellow one of such stoichiometric compatibility classes in each case. With orange, it's the steady state, the steady state set. Okay, and we see that in the case of the phase portrait for reaction A, there are two, the intersection between the steady state locus and such, for instance, the yellow stoichiometric compatibility class has cardinality 2, whereas in the image under the affine map, the phase portrait shows that we don't have multistationarity at all. Always have precisely one intersection point. This is an example. We were hoping that this was true, but that the multistationarity will be preserved, but it turns out this does not happen. Moreover, we also wondered what happened with the limit cycles, and here's another example that all the details, so you can read more details in the paper. Starting with this network from A, apply a rotation. So we rotate it just with 60 degrees. Actually, this network A has even a name. It's a version of the Brassellator. Maybe you can read more about such networks in Feinberg's book, Chemical Reaction Network Theory, for instance. So there you see many such examples. You also saw last tutorial, so many nice examples from Beatrice. Okay, so if you take this reaction, it has a limit cycle. You see here in the phase portrait. Once we fixed here some rate constants. But if you rotate it, the limit cycle disappears. Actually, that's what I said here. Once you rotate, there is no limit cycle, so that's a counterexample. Moreover, also one can prove that if before we had an unstable steady state, it became stable. So also the property of so the stability is lost, or so the property concerning local stability might change. So in conclusion, invertible affine transformations do not in general preserve qualitative dynamics, but they preserve what we were interested in, disguised spheric loss rate. Okay, for the third part of the talk, we might think of projective transformations. So we are now passing to the case of generalizing what we saw before. We were looking at so always invertible but affine transformation. What happens for projective ones? I recall that we saw that a necessary condition for preservation of dynamical equivalence was preserving the collinearity of vertices of the network, and now projective transformations also preserve collinearity. Okay, so let's see some examples. first of all, I thought it's important to give a definition just to fix also notation and what is an invertible projective transformations on Rn. This is a fine expression of such a transformation. It's a function of this form. So we take Li to be of this shape, where all the coefficients Ai from a matrix n of shape n plus 1 times n plus 1 come from a matrix that is invertible over R. And once you have these forms, okay, we get such an expression in terms of for each y in Rn. Again, we need to define what we consider the image of a graph or of a network under such a projective transformation that is invertible. As before, what is the new graph? So what are the vertices, what are its edges? Again, the vertices are obtained by taking the images of vertices from the previous network, and the edges, again, just connecting these new images. So in terms of graphs, abstractly, this is the definition for the image of a graph under invertible projective transformation. Just like before, by definition, we consider that when we talk about this image, we inherit, so the new graph inherits the reaction rate constants, Kij, for respectively for each reaction. So let's look at an example here. If we consider such projective transformation, here it's a simple one. What happens with this network? We come back to the network that we looked at last lecture. It's the quadrilateral on a line, we call it. So these vertices that are of coordinates 0, 0, 3, 2, 1. So here is 2, 1, 1, 2, and 3, 0. Applying this map, just direct computation gives us the new vertices. You see that it's interesting. They change a bit their respective positions. Okay, y1 comes here in this position, and y4 arrives in the right hand side here in the bottom. Of course, collinearity is preserved, and we get P of this graph, where P is this. Now, what can we do? We can compute the disguised historic locus, and here you can read the arguments for this, or we can discuss during the tutorial as an exercise. Compute the disguised historic locus for P of G, and we will find out there is, at least we find some precise vectors of rate constants that lie on the disguised historic locus of P of G, but that are not on the disguised historic locus of the initial one of G. And how we do this? We will actually need the characterization I gave in the previous lecture for computing the disguised historic locus for the quadrilateral on a line. Specifically, it was that decomposition into 4 chambers that gave us different inequalities for the case, all these cases here. So we knew precisely algebraically we had the precise expression for the disguised historic locus completely characterized for the quadrilateral, and that is what helped us actually search for such a vector of rate constants that's outside the disguised historic locus of G. We started by negating such a property from before, and so which such vector would verify actually the properties for the other one. It was a game. During the tutorial, we'll look at this. Okay, and another, so this example as a conclusion is saying that projective transformations don't preserve the property of being disguised-storic. So we stopped now. Once we saw this, we were convinced that affine transformations are the best class that one could think of when working with complex balancing, at least in this context. Now, what happens? Okay, here in general, disguised-storic, but what happens with complex balancing? More precise, more in particular. So here it was dynamically equivalent to complex balancing for disguised-storic, but what about precisely complex balancing? Now, in this example, I didn't draw a picture. One can imagine where in R to the 1, the graph with 3 vertices, 0, 1, 2. And we consider the complete graph on these 3 vertices. Now, we define an invertible projective transformation that is, how to say, pointwise defined on these 3 vertices. Let's just call A the image of 0 by this transformation, B the image of 1, and C the image of 2. Okay. Now, since this is a complete graph on the vertices 0, 1, 2, we saw last lecture what happens with a triangle on a line, what we were calling before triangle on a line. It was the first example, and we checked, we know also from the tutorial last time how to get this toric. Here, actually, we are talking about the toric locus. So actually, this example, you might think of it, what happens with the toric locus under the projective transformation. Recall we got this using matrix 3 theorem, or a simplified version of that, where we were making that change of, here the capital K's are those come from those change of variables from the spanning trees of your network. I explained in the tutorial. So here is the complex balance condition on this graph G. But now, question, what is now the complex balance condition on the projective transformation, on this projective P of G? With the same rate constant K and same change of coordinates capital K, we had to use here use some theorem that you can find in the paper by Peliu, Capelletti, and Youth from 2018. By the fact that we get these ratios that we can find here, directly applying this theorem, I don't state it here, we just get that the complex balance condition for the image is given by this equation. A, B, and C are these images from our invertible projective transformation. And you see that generally, so for generic case, the two algebraic sets, so the one for P and the one for the toric set for locus for P of G and the one for G, are not equal when we don't have this equality A plus C equals to B. When A plus C is different than 2B, this means a generic choice, right, of the projective transformation P that was given by these A, B, C values, real numbers. We don't have that equivalence between the toric loci for G and P of G. So in general, for generic rate constants, where G is complex balanced, P of G is not. So, this example shows that complex balancing is not preserved under projective transformations. And why we take all these examples? Because the affine transformations were preserving all these properties. They were preserving the disguised toric loci, they preserve the complex balancing property, and what else did we show? We showed that also in the beginning that invertible affine transformations also preserve dynamical equivalence. So let's see what happens under projective transformations. I already announced here in the title, they do not preserve dynamical equivalence. Why? How can we see this on an example? Again, since it's a graph in r to the power 1, I don't draw it. Start with the complete graph on 3 vertices, 0, 1, 2. So again, you can think of the triangle on a line in some sense. Now, if we say G with, so remember that in the triangle on a line lecture before, I showed you that you can find a system that is given by the same graph, but with different rate constants that are such that the new system is dynamically equivalent to the initial one. And maybe you remember I started with the triangle on a line, then we went, this is yeah, we went to a network that has one reaction per source, and then this, and we changed accordingly the rate constants, and then the network with one reaction per source, we also rewrote it, again changing the rate constants, in the shape of a complete directed graph on 3 nodes, and showing that this one, the new one, was toric for any change, any rates of any constants, rate constants. Maybe during the tutorial I also recall this, because there we were using the intermediate value theorem in the pullback function that we saw. Otherwise, you can check this again in the video of the talk. So recall that we had there the possibility to find dynamical equivalence, but preserving the graph. That was an interesting example. So we don't need to change the graph. Sometimes we need just to change the rate constants. In other cases, we preserve the rate and we change the graph and so on. Now, what we can do, we denote by, so for each reaction, ij, let's denote the difference between k and alpha by beta ij. And then take the vector of, so you see, this is the complete graph on 3 vertices. It has 6 reactions. Well, then we get a vector of 6 entries. If you check, it's really just the matter I was saying of changing the rates accordingly. In a compact way of writing this, the fact that G with the rates K and G with the rates alpha are dynamically equivalent, based on what I was explaining, if and only if the new rates alpha satisfy these equations actually. So written in this form, just check the vectors, what happens here. Keeping in mind that it's the same graph. So if you plug in these equations, you will see that it's true. So G with K and G with alpha give rise to dynamically equivalent systems if and only if, okay, beta is not 0, okay, and you get these relations 3 here. Again, let's consider an invertible projective transformation defined at these points 0, 1, 2, and just denote by A, B, and C the images of the vertices 0, 1, 2 by this projective transformation. Again, we here suppose this condition A plus C is different than 2B that we encountered before, because we need this in order to have, now we want this dynamical equivalence. So just pick A, B, and C in this way. And we obtain now a very interesting thing. So what we look at now, we look, if before we had G with K and G, the same graph with alpha, what happens with P of G and considered again with the rates K and alpha? Turns out that the new graphs are dynamically equivalent, so the images, if and only if we have this matrix representation. This is not very difficult, just by hand you can check. Okay. Beta, of course, we considered it non-zero. A, B, and C, we consider them distinct. We have an invertible projective transformation. So the non-zero vector beta satisfies both these 3 and 4 relations, if and only if we have some algebraic constraints on A, B, and C. Okay? And these are the algebraic constraints. We have 3 of them, and equivalently, we can conclude that gives us precisely A plus C equals to B. But, okay, so A, B, C satisfy both dynamical equivalence between PG and between the images and dynamical equivalence between the initial graphs, if and only if A plus C equals to B. But we suppose that A plus C is not to B precisely because of what we saw previously in this theorem. So we got a contradiction. So P of G with the rate constants vector K and P of G with the rate constants alpha are not dynamically equivalent, although G with the rate constants K and G with the rate constants alpha were giving dynamical equivalence. They were giving rise to dynamical systems that are equivalent. So with this example, we see that invertible projective transformations do not preserve dynamical equivalence. And it was nice because we had the chance here to see in action some properties from last lecture about the triangle on a line that hopefully, if time permits, we'll look again in the tutorial. And also, I think it's interesting that we also saw this counterexample here, showing that the disguised toric locus is not preserved in general by projective transformations. Again, using what we saw last time, actually the quadrilateral on a line network. Again, concretely during the tutorial, we can see the computations. So now I'm done with all the counterexamples, and I thank you for your attention. Maybe before this, I just want to say, again, I recall that the terminology and everything that I talked about, these toric dynamical systems, you can find in this paper together with Rustenga, Imoncuzi, and Crăciun. Okay, and all the computations we will see in the tutorial. So we can already check during the break some of the exercises for the tutorial, because those will be from this paper. Moreover, what I talked today is based on this paper by Hake, Satriano, and myself and you, the disguised toric locus and the fine equivalence of reaction networks, published in 2023. We were based on this paper by Feliu, Capelletti, and Viuf that Okay, and this I didn't speak about the first two preprints. So with that, I will stop.
Thank you very much. Thank you. Thank you, Miruna. Are there any questions from the audience? Okay, I think everything is clear and people were asking questions along the way. Thank you very much, Miruna, for your lecture, for your course, and definitely these things are completely new for many, including myself. And I really appreciate that though you were online, but you tried to be as clear as possible through your presentation. And just to address all the participants, those who are interested in following the further progress in this particular direction, so all the lecture notes and recording of Miruna is placed on the website. And moreover, you can also see the references, and you can approach Miruna for further questions. Thank you, Miruna. Thank you very much.
Thank